Welcome back to the podcast, everyone. This is Mark, and I am buzzing today. We're talking about something that's been on my tech radar for years, and it's finally delivering.
And I'm Jenny, ready to unpack all this excitement with you, Mark. You've been hyping up graphene for what feels like forever, and it sounds like 2025 is the year it truly steps into the limelight. What's got you so revved up, really?
Jenny, this is big. For decades, graphene has been this incredible wonder material, super strong, conductive, just one atom thick. But for electronics, it had a problem. No band gap. It's like having a light switch that's always on. You can't build a computer chip if you can't turn the electrons on and off. But now, Georgia Tech. They did it. They created the first functional graphene semiconductor.
Okay, wait, let me get this straight. So for 20 years, the dream of graphene replacing silicon in our devices was stuck because you couldn't effectively turn it off? And now, suddenly, they cracked the code? How significant is this, really?
It's a considerable shift. Consider silicon, the foundation of modern electronics. It's hitting physical limits, heating up, getting harder to shrink, nearing its ultimate performance capacity. Graphene, with this band gap advance, now has the potential to step in and push past those limits. We're talking about electron mobility 10 times faster than silicon. Walter de Hesser, the Georgia Tech professor behind this, put it well. He said, "It's like driving on a gravel road versus driving on a freeway." Quote, efficiency, less heat, higher speeds. It means processors that can run at 100 gigahertz, with 50% less power consumption. This extends Moore's law well beyond what we thought achievable with silicon.
10 times faster? Less heat? That sounds like the holy grail for everything from your smartphone to massive data centers. But if this is such a powerful material, why does it feel like we haven't seen graphene in every device yet? Is it still incredibly expensive or difficult to produce, or something?
That's the next part of the story, Jenny. The production side has really been catching up. Historically, yes, it was expensive and difficult to manufacture at scale. But by 2025, which is, right now, the projected cost for CVD graphene, that's chemical vapor deposition, is going to drop considerably. We're talking $30 to $50 per square meter. It was over $100 just 2 years ago. That 50% cost reduction opens up so many doors for widespread adoption.
That's a major price drop. So, if the cost is coming down and the performance is notably superior, where are we going to see graphene first? Are we all getting graphene phones for Christmas? Or is it more behind-the-scenes stuff, like in specialized industrial applications?
It's a bit of both, but with an interesting split. We're seeing two main tracks emerge. On one side, in places like Europe, the focus has really been on medical applications. The EU Graphene Flagship, a substantial funding program, has poured resources into this. Companies like INBRAIN are developing graphene FETs, field effect transistors, that can actually detect individual neuron activity for things like epilepsy treatment. These medical devices can be smaller, more biocompatible, and have lower purity requirements for the graphene itself, so they've reached commercialization faster in that space.
That's fascinating. So, while the US seems to be pushing the computing side, Europe is focused on putting graphene into our brains. Are brain-computer interfaces the major application that makes graphene mainstream? Or is that still very niche, you think?
In Europe, for medical devices, it's becoming less niche. INBRAIN's devices are already going into human trials soon, with an eye towards treating neurological conditions. They've passed ISO certification, which is a significant hurdle for medical tech. But in the US, the emphasis is clearly on the high-performance computing side. We're talking AI accelerators, next-gen processors for data centers, pushing the limits of speed and power efficiency, where silicon just can't keep up. It's like a technology race, but with different battlefronts, if that makes sense.
A technology race for atoms. I appreciate that analogy. Speaking of which, with all this talk of high-tech production and atomic precision, how do they even ensure the quality of this stuff? One stray atom ruins the whole chip, doesn't it?
You've pinpointed a crucial aspect, Jenny. That's where the other major advance comes in. Defect control. For graphene to work in semiconductors, you need material that's nearly perfect, less than 0.1% defect rates. For years, This was incredibly hard to achieve, but now they're using AI. AI-driven atomic repair, sophisticated machine learning algorithms that can detect and even correct atomic defects during the growth process. So it's not science fiction anymore, it's happening on the factory floor. And it's what's enabling this less than 0.1% defect rate.
That's something else. So AI is building the very materials that will power future AI. It feels almost poetic, doesn't it? So with this band gap solved, costs falling, medical applications thriving, and computing uses gaining traction, is graphene going to completely replace silicon then? Or do we still need our reliable silicon chips?
That's a good question, and the general consensus among experts is no. It won't entirely replace silicon, at least not in the near future. Silicon has decades of infrastructure, substantial labs, established processes. Graphene's role is more about extending what silicon can do, or complementing it. Think heterogeneous integration. You might have silicon for the main logic, but graphene for ultra-fast interconnects, or specialized components for high-frequency signals, or thermal management. It's about creating better systems by combining the strengths of both materials. Like a complementary team.
A complementary team. I like that. So it's not a silicon vanquisher, but more of a silicon enhancer. What does that mean for the next few years? What kind of devices or advancements should we be looking out for, specifically?
Oh, the future here is quite something. We're talking neuromorphic computing. Chips designed to mimic the human brain. Graphene's analog properties are well suited for this, allowing for significantly energy-efficient AI. Samsung already has a prototype in 2025 using graphene memristors to mimic synapses. Imagine AI that learns faster and uses a fraction of the power.
So brain-like AI chips, that's already in prototype? Wow. What else is on the horizon then?
Ballistic electron transporting graphene also makes it quite intriguing for quantum computing. It creates ideal conditions for topological qubits, which are more resilient to interference. Microsoft's Station Q project is looking at using graphene substrates for 1,000 qubit systems. And because it's so thin, you can stack graphene layers, creating incredibly dense 3D integrated circuits, something silicon struggles with. TSMC is already looking at using graphene interconnects between stacked memory and logic layers in their 2026 roadmap. It's moving quickly.
So neuromorphic, quantum 3D stacking. It sounds like graphene isn't just a material, it's enabling entirely new computational models. It's genuinely moving beyond the simple, faster chip narrative and into something much more foundational. Mark, you've really presented a compelling case this time. This is genuinely interesting.
I thought you'd come around, Jenny. It genuinely feels like we're at a turning point. After years of promises, the pieces are finally aligning. The advances, the cost reductions, the industrial integration, it's all converging. The next few years are going to be fascinating to observe as graphene transitions from lab success to commercial viability.
Indeed, and we'll be here to track every step of that journey. That's all for this episode on the graphene unfolding. Thanks for tuning in, and we'll catch you next time, everyone.
Thanks, everyone. Stay curious.